Okay, so let's start. Today I'm going to finish basically the introductory part of the course. We are showing, I discussed actually two examples of problems where you can write down a classical field theory and then quantize it and get a description in terms of quasi-particles that behave like free gas in a sense, at least in the simple examples that I've given you, and everything is described in terms of ladder operators which are creating and annihilating particles. The first example we already finished, so I just mentioned it. So it is phonons in a one-dimensional chain of masses on springs. And what we saw is that, so we started from some mechanical problem of an elastic string of masses connected or interacting with each other. And we replaced the coordinates and momenta of individual atoms by new degrees of freedom. And in the final stage, we got a Hamiltonian that is completely given in terms of collective modes of vibrations of the string. And these are the quantum entities that carries energy here. We refer to them as particles that are, we call them phonons because they have to do with sound waves. And the form of the Hamiltonian is this. I'm just writing the result. Where omega k are frequencies that are linearly proportional to wave number with a velocity v, and v is the velocity that comes out of the elastic stiffness and the masses of the atoms. And these operators, A and the A dagger, are annihilation and creation of phonons, each for an individual mode k, and they obey the following commutation relations. So AK and AK prime or their dagger are always commuting for arbitrary choice of K and K prime, but AK prime dagger give you non-trivial commutator 1 whenever K is equal to K prime. And this, the behavior of the particles that we get in this description is that they can occupy any quantum state by as many identical particles that you like. Therefore, they behave like bosons. They have a boson statistics. So today, and then we also concluded, just to summarize this part, that in fact we can describe the system in terms of states that are expressed in a Hilbert space of the following type of states. I can write them as a sequence of occupations of all the possible K states. and explicitly they are given by the product over all k of, there's some normalization.
Product, right?
What?
Outer product.
No, this is not, yeah, if you like, it's an outer product, but this is just one state that I'm writing here, writing it here explicitly, but what it means is that, yeah, each state is occupied by some number of, integer number of particles. The nks are larger or equal to 0. Okay? So we write it here. Each I is some non-negative number, integer number, and there is, this is how they look. This is a normalization factor, and dagger to the power nk acting on the state 0, where the state 0, which we also name a vacuum, is just the 0 occupancy states, where all the k states are empty. Okay? That's the vacuum, and we create particles above the vacuum by applying the operator A dagger. And the set of all states of this form for any choice of nkis that are integers larger or equal to 0 is building our Hilbert space. And many particle states in these systems we can write in this form. We can also express any physical operator that we are interested in terms of these operators, and therefore we can calculate expectation values just using the algebra rules. Okay? So that's a very useful expression for the system, and the fact that it has such a simple form follows from the fact that the Hamiltonian is quadratic in the field. Okay, so therefore we can write it as a free theory, and of course this is a very special case. Most systems are more complicated, and we'll discuss it. Most of the course we will devote to actually study more complicated cases. But we start from a description. The second problem that for which we already wrote a field theory, but we still have today to finish the part of the quantization, is the electromagnetic field. There, the way we got into the field theory was very different. It was not starting from a microscopic, concrete Hamiltonian that you already know from single particle physics, but we started from some equation of motion, these are Maxwell equations, and from knowing some symmetry rules that give us guidelines how to guess a theory. Okay, and we guessed a theory, and we arrived at this Lagrangian, and now I'm going to write a version of it that we started writing last week, and that is a special case for the gauge, the Coulomb gauge. Okay, so I remind you that in electromagnetism, let me first write the more general. The more general theory is so the Lagrangian is given by F mu, F mu. Maybe there's a factor of minus, I'm not sure.
You mean one with stopping this?
Sorry, this is wrong. Okay, this is the first term, and this is in vacuum, namely when there are no external currents. Otherwise, there's an additional term, A dot J, but I'm just taking the vacuum, okay? The part that only depends on the electromagnetic field, no charges, no currents, okay? And this is the one we are focusing on. And this is a complicated object in general because it has many components, and we're going to have many terms, but we can use the freedom of gauge choice to simplify. So we chose the gauge that for the vector potential A, that the electrostatic potential is 0, and that the vector potential, the three-component vector potential in space, has divergence 0. This is called a Coulomb gauge.
You choose it locally or globally?
No, it's
Global condition.
global. Yeah, it's a global condition. Coulomb gauge, and not going through the algebra, one can show that for this gauge choice, you get a very simple model. I think you still have the. See, yeah, you have 1 over 8 pi here, and the first term is time derivative of A minus the curl of A. And it is easy to recognize that the first term is electric field square, the second term is magnetic field square. So if you convert it to Hamiltonian, you get the familiar energy density E squared plus V squared, okay? Okay, so that was our starting point, and now we are going to work with this, but we want to bring it to a more convenient form, taking into account that here you have a space derivative. In fact, there is a curl of A. So there is a space derivative, and when you have a derivative in a real space, it's a non-local term in real space. But then if we do a Fourier transform, we can replace it by a wave vector. Okay, so just the same stage, that's the same trick that we did for the elastic chain. The time dependence for now I still want to leave because I want to stay with the notion of time derivative of the field. Okay, so what I'm going to do now is to define A, which is a function of R and T. I'm going to define it as a Fourier series. Let me write here a normalization factor, where here this capital omega is just the volume of the system. Okay, so let's assume that there is an electromagnetic field. It lives in a vacuum. There's no matter field, but it's generally, let's assume that it's in some kind of a finite volume. We can always take the volume to infinity. And then we have a sum over k of alpha k e to the I k dot r. Okay, this is a Fourier expansion where the alpha k is, so we were going to replace the description of the Lagrangian by something which eventually will have the form as sum over k of something that depends on these alpha k's. Okay, that's the idea. Now, so the problem is still a little more complicated than what we had in the phonon case in 1D. Why? Because now A is a 3 vector. It's a vector in 3-dimensional space, and therefore so are the alphas. Okay, so there's not just one alpha. In principle, it's a vector in 3 dimensions, so how many components it has? 3, right? But actually, that's not quite true. I mean, of course, it is true, but I'm claiming that one of the components is 0. Why is that? Very good. So remember that this form of the Lagrangian is biased. I mean, it's correct only for the choice of gauge that we wrote here. Meaning that this vector potential A has to satisfy that its divergence is 0, right? So I have to apply the constraints coming from the gauge on this expression, okay? And when I apply the gradient operator on this object, where is the space dependence here? It's only in the exponent, right? So when I apply a gradient, I get a factor of ik. So I'm going to get inside the sum, I'm going to get k vector dot alpha for each k. Okay? So, for each k, this implies that k dot, in order to get 0, I need every sum every term in the sum to be 0, right? And so, for every k, actually, let me now be a little more careful because the k's are also vectors. So k dot alpha has to be 0. Okay? So what does it mean? You give me a k that has some direction. Let's say this is the wave vector. So it describes the propagation direction of this mode. So in order to satisfy this, what has to be the direction of alpha? In order to obey, the scalar product to be 0, it has to be perpendicular, exactly. So the alpha must lie in the plane that is perpendicular to, okay, so alpha is somewhere on this plane. It can be anywhere on the plane, but it's perpendicular to k. Okay, that's actually what it implies, that alpha k perpendicular.
If k is constant with time, that means alpha is on a plane.
No, k is of course constant in time.
Therefore, alpha is constantly on a plane.
Yes.
Yeah. With time.
Right, right. But we want to notice that we don't want to define some global coordinate system x, y, z, on which it's convenient to describe all the alphas. Each k determines its own, if you like, xy plane, for which, and you know that the alpha has to lie on this plane. And because it's a 2-dimensional plane, how many components or how many independent orthogonal vectors we need to define it? Only 2. Okay? So in fact, the most general assumption about alpha is that it's going to be a sum of two polarization modes. I call it polarization modes because it describes, if you relate it to some electric or magnetic field, it gives you some direction of the polarization of the field with respect to K. So there are two of them. I denote the index by lambda, 1 or 2. And for each alpha, I have a scalar field with two indices, which depends both on K and on lambda, times epsilon K lambda, where the epsilon K lambda are two unit vectors on this plane that is perpendicular to K. In other words, they satisfy that for each K, this vector product of epsilon 1 and epsilon 2 is the unit vector of K. Okay?
Wait, what is K1?
So they are just unit vectors
On the plane.
on this plane.
Okay,
Yes.
okay.
And they are two orthogonal. We can choose them to be orthogonal to each other, okay, such that their scalar products. So, for example, in this picture, we can, if I just extracted the plane, and this is the 0, so I can have, this is going to be epsilon 1 and epsilon 2, okay? But this is the plane perpendicular to K, okay? And of course, the direction of the plane depends on K, okay? So that's the definition, if you like, of the epsilon. And each alpha I can write as a summation over the two modes. And now I'm plugging it into A, and let me just write the final results. What do I get when I plug it into the Lagrangian? I actually get now something very simple, because all these the variables eventually that appear in my theory are going to be these scalars. The scalars alpha, K, lambda, that have two indices, and there are many of them, of course, but the theory will be separable in terms of these terms. That's what you find if you just do the algebra. Okay? So let's write down what we get. So get a Lagrangian that has the form sum over K and lambda, where lambda again runs over only two polarization directions, and actually, because of the normalization factor that I chose, sorry about that, let me add here a factor of half outside, sum over K and lambda, of what do we get inside the sum? From the time derivative, we're going to get first the product of time derivative of alpha at K and minus K for each lambda, minus omega K square alpha K lambda alpha minus K lambda. And that's it, where What is omega k here? Can you guess what it is? Yes?
Well, the half factor is coming.
Never mind, okay? It's because here I have a square root of 4 pi, and it's actually 1 over 8 pi, and so the 1/2 remains, but
okay,
it's a matter of definition. The volume is what gives you, after you do the Fourier, you plug in the Fourier transform, integrate over R. Okay, so okay, and the integration over R, and that's the important thing. It gives you once again a delta of k and minus k prime.
And
so
there is not any factor in the numerator of square root of pi?
No, in this, no, you can do it. I encourage you to do the algebra. Believe me, this is what you get. You trust me. And I left a factor of half here just that it will have the form that you're familiar with, because soon we're going to turn it into a Hamiltonian description. But first, what is omega k? So in fact, it is the way we've written the theory, it's actually the absolute value of k. Okay, but
because
this is because C is 1. So we started from a theory that assumed C equal 1. And in fact, if we bring back the units, of course, C will appear here. Okay, so this is actually, to be a little more careful, this is what it is. It is just the frequency of a photon with wave vector k, right? Or the frequency of a free electromagnetic wave with the velocity of light coming. Okay, yes?
What happened to the integral?
The integral is, so if I plug it here, the exponent, and I get a delta function.
Oh.
And that's why I need the factor of volume to cancel the integral over R. Okay, the integral here is over the volume. Okay? So, so that's the result, and notice how similar it is to what we got for the phonons, right? It's really very similar, and soon we are going to write the Hamiltonian, and it will look even more similar, except one of the new elements here that we have more indices here. Okay, we have more types of modes. We could also have it, by the way, for phonons, because of course in our derivation we just looked at the longitudinal ones, but they're also transverse. And you can have also different modes with the same wave vector for phonons. Okay? But the nice thing is that they can be separated. Okay? Okay, so that's a Lagrangian. And now, in order to do the quantization, what is the prescription? First, you want to go to a Hamiltonian description. Why Hamiltonian? Because in the Hamiltonian, you have coordinate and their conjugate momenta. This we already know how to quantize. They have canonical commutators. And once we have, in our case, momenta and coordinate, we can also mix them to create AK and A dagger. Okay? So that's what we do. First of all, the first stage to get the Hamiltonian is to derive what is a momentum operator. So notice we are talking about electromagnetism. So the notion of momentum is not naturally built into our theory in this case. In that respect, it's very different from what we had for the mechanical problem. But we formally know how to define a momentum for any field theory where you already have a form for the Lagrangian. Because what is the momentum? I remind you of, okay, let me just make some more. So we can now define a momentum operator, pi k lambda, as the derivative of the Lagrangian with respect to alpha k dot. Okay, so these are our fields. This is the canonical definition of a momentum. What do we get in our case? If we take the derivative.
Alpha dot minus k vector lambda.
Yes, exactly. So we get alpha dot, but not of the same k, of minus k. Okay, that's the momentum, and yeah.
A factor comes because you are summing on all directions, and then you summing on plus k and minus k.
Yes.
Okay. Okay.
That's one way
okay,
to.
okay.
Yeah, that's true. That's true. Yeah. But again, it's also a matter of definition,
Yeah,
right?
yeah,
In a sense.
because of like if k is minus k, you have also another thing that.
Right.
Yeah.
Right. Yeah.
The momentum shouldn't be half alpha dot minus k?
No.
No, yeah, but
That's the definition.
You sum on all k, so
Ah,
you
okay,
sum
okay,
also
okay.
for minus k.
Yes, exactly. For any k, you already have.
That's why.
Minus k
should
actually
probably
appears twice.
normalization.
That's
Okay.
right. That's why you want the factor of half. Exactly. Okay. So, great. So, and then, therefore, the Hamiltonian is given by the Legendre transform, which is a sum over k and lambda of. First, I have a pi k. I'm just following the definition. Minus L. Okay, it's this minus L. You do the algebra again, and not surprisingly, you get something that you're already familiar with. So it's exactly like the harmonic oscillator problem, but but now the parameters are a little different. It looks like this. It's 1/2 sum over k and lambda of pi k pi of minus k plus omega k square alpha k alpha minus k, which is nothing but the potential energy, just like you have here, but with a plus sign. This is, sorry, so that's the,
That's already slit there.
yeah,
So
okay, let me try to avoid this corner. Okay, right, so this looks very much like the Hamiltonian of the phonons that we had before in terms of momentum and coordinate, but the first term is exactly the form of a harmonic oscillator of the kinetic energy, so to speak, but without a factor of 1 over m. So, if you like, this is.
So the theory is free.
The
of
theory
mass.
is there's no mass. I mean, by the way,
Free
the
from
capital M, this mass, has nothing to do with the mass of the particles that come out of the theory. And going back to the phonon, the phonons, what kind of particles they are? They are relativistic particles. They have a dispersion that omega is linear with k. Energy is linear with momentum, not quadratic. So in terms of kinematic rules, it's like a relativistic particle if the velocity of light is replaced by the velocity of sound.
So all the statistical mechanics we done on photons is also valid for
exactly. Those? It's exactly the same calculation, okay? Right? Actually, you know, the calculation of the black body radiation and the calculation of photons in a cavity, it's the same calculation, okay? Okay, except for parameters. So, so these are massless particles in terms of their relativistic kinematic rules, and the same for the photons. And the capital M, which is just a parameter, happens to be 1 here. And so the M equals 1, and the way we defined our theory with C equals 1, but in fact, we can bring it back and call omega C times K, right? It's just the same omega, okay? And now we can do the same trick we did for the phonons, because it's exactly the same form of the Hamiltonian, just copy-paste the parameters. In fact, the fact that some of them are 1 only simplifies the things. And if you remember, how did we get this form? We took some linear combination of the coordinate and momenta that defines the ladder operators. So here we are going to do exactly the same thing. Let's write it explicitly. So this we no longer need. We just write here that omega k is k, or c times k. Okay? Good. So we define now an annihilation operator, ak lambda, to be let me, you know what, I'm going to use, I'm not going to define one more quantity, let me just write it in the following form, okay? This is square root of this omega k over 2h bar times the alpha plus I times, I think it is 1 over omega pi of minus k and lambda. Okay? That is the definition of A. It's completely equivalent to what you already saw for the phonons. And therefore, a dagger follows directly. It's the same normalization factor times alpha dagger of k lambda. What is alpha dagger?
Alpha minus k.
Exactly. So we again have the same property that all these fields in real space they obey their physical fields that obey that alpha equals alpha dagger. Therefore, their Fourier components obey that alpha k dagger.
Yeah, it's because it's transformation.
Exactly. When you do the Fourier transform, when you dagger it, you see that there is a minus sign on the k. Okay? And that's why, if you look at this Hamiltonian, you can write it actually as pi dagger pi and alpha dagger alpha for each k.
Just because e to the ikr, the I switch in the sign.
Exactly.
So
Right.
now it's minus k.
Exactly. And therefore, this is alpha minus k lambda minus I of omega k times pi of plus k lambda. Okay? Right, so that's this is the transformation that we use, and plugging it into the Hamiltonian,
Wait,
we
pi,
get the
just question, pi and omega have k, not minus k?
yeah, because also pi dagger
Is-
of
okay,
minus
it's
k
supposed to be-
is pi k.
Yeah.
Okay, so you see it's very
They need to be
symmetric.
real values.
Yes.
Yeah.
The pi, yeah, the in real space, the coordinate and moment are real values. Okay?
Wait, here it's minus? That
This is minus. Here it's minus. That's not a mistake. It was the same for the phonons, by the way. Okay?
okay.
All right, and with this definition, let's go back, take this Hamiltonian, and you obtain the final result is sum over k and lambda
We got
of h bar omega k okay, it's exactly the same algebra that we have seen, and by the way, the fact that the mass capital M is 1 doesn't have any effect. You see that that's, by the way, a signature that the value of M is not an important, it's not an important
The theory is
parameter in the
independent of
theory. Is
the
exactly.
mass.
Actually, the only place where it comes into the physics is into, in the case of the mechanical problem, the mass determined the velocity, because the velocity of sound is the square root of stiffness over mass. Okay? So these are well the parameters. Here in electromagnetism, there is only one parameter, the velocity of light. There's nothing else. Okay? Good. So, all right, so this is it.
So that is a good sign.
That's a good sign. Yeah, so that's the theory. What does it tell us? That the electromagnetism, in the absence of matter, because once you put matter, you can get all sorts of complicated corrections. But just describing electromagnetism in vacuum can be converted to a quantum theory of quantum particles, and these quantum particles are the photons. We already know them, okay? At least we learned about them, but this is how we actually get them, okay? And they are the real particles of the system, in the sense that the electromagnetic field can be described as an ideal gas of photons, okay? And they have statistics of bosons.
We know also the
And,
equation of state of photon gas.
Yeah, right.
Equation of
So if you do statistical mechanics with them, you work with them as an ideal photon, ideal boson gas. Okay, that's how you get black body radiation and all of that. Okay. All right. So. Yeah, so before actually I made a mistake when I said that for the photons, from the photon description, you get the black body radiation, which has to do with electromagnetism. From phonons, which have exactly the same statistics, you get the specific heat of solids, for example, obeys exactly the same formula. Okay? It gives you an energy that goes like temperature to the power of 4. All this mathematics follows from the same calculation. Okay? Except that there are parameters, and the parameters are related to this velocity, and that's why you get the Debye temperature and all that you don't have for the photons. Okay? Very good. Okay. Yeah. So some of us can really measure it. Right. Okay. So once again, as long as these are the building blocks of our world, we know how to write any wave function, and we think of a wave function that is a many-body state of many such photons. They can occupy different modes, and the most general state is once again going to have this form. So if I'm describing the spectrum of the photons by some hierarchy of states, let's say according to their energies, h bar omega, then the general state may have some occupation of 1. It can have 4 particles at K2 and 2 particles at K3, and so on and so forth. And this kind of state can be expressed as some occupation of K1, but there is also a lambda, right? So there's a lambda, what do you call it? Some occupation of the same K, but lambda equals 2. Then AK2, 1, and okay? All right, so, and the states are completely defined by the occupation of each mode. And there is a vacuum state. The vacuum that is really our vacuum, if you like, is the vacuum of the universe. Is this. Okay, it's empty, completely empty. And by application, repeated applications of a dagger, you can create any such state. Okay? So it has this form, except that instead of just one type of quantum number, now you have K vector and lambda. That's all. Okay? Everything is the same. Okay. Good. So that's a very nice example. Actually, we saw 2 physical examples that are very different from each other. If you think of the microscopic description and the degrees of freedom that generates them, nevertheless, they both have a very similar description. And we could also think of corrections to this simple Hamiltonian, to these simple Hamiltonians, which take into account processes where you have interactions between photons or interactions of photons with some other particles.
Now they are independent.
Right. Now they are independent. That's because we started from the theory for the vacuum, I mean, of matter. Okay?
You can add x to the third or something to the Hamiltonian.
Yeah, right. You can imagine processes where you have, for example, if you do have matter field and you pass an electromagnetic wave through a medium that has some dielectric constant that is nonlinear, you can generate interaction terms, okay? And you can definitely do so in an elastic medium. If you go out of the harmonic approximation, there are always corrections, okay? But in principle, we can write any physical operators using these building blocks, the A and A dagger operators, okay? And at least the problem will be well defined, and then how we calculate is a separate problem. Let's assume that there are some techniques, but we know how to define the problem. We don't need to go back to the roots, okay? Okay, so we would like to do that in more general physics problems of many body. And let me give you some idea why we really need a new language if we want to discuss a problem of many particles, many quantum particles that are either bosons or fermions, and they are identical particles. And because of that, they have non-trivial rules which have to do with their quantum statistics. Okay, so I want, before I go to define the formalism that we're going to work with, I want to remind you what is the difficulty we are facing if we stick to what we learned in our undergraduate quantum mechanics, which I remind you focused mainly on single particles that have to obey some Schrödinger equation depending on a potential. Okay, so there's a lot to erase here. Okay, so so in general quantum mechanics, what is really the problem? You have some Hamiltonian that describes the particles, and if you have more than one particles, this Hamiltonian can be written in terms of coordinates of all these particles, and there is a set of single particle states. Let me denote them by lambda. So it's a single. And the lambda is some quantum number such that the states lambda, where you sum over all the possible lambdas, are a complete set, okay? They span the Hilbert space of a single particle.
The particles are the same or identical?
So, oh?
The particles are identical?
Yes, so the lambdas are just single particle states, okay?
Yes, all particles.
Yeah, let's assume that, yes, we are talking about one type of particles, identical, either electrons or photons or what have you. Right, so the wave function of each particle can be written, or any wave function can be written as a superposition of the lambdas. Okay? And what are the lambdas? Usually you want them to be some eigenstates of some single particle Hamiltonian. Okay, I denote it by H0. This will be our convention.
Lambda is out the product of
lambda is a quantum number, which in fact it can be anything, because it just
It's
I mean,
eigenstate
what
of
it is,
the
it
Hamiltonian.
can be arbitrarily chosen, provided that the states span the entire Hilbert space. But usually you want to define it to be something that
Can you,
diagonalizes at least part of your Hamiltonian, right?
so my question is, you can write before that you had nki
Yeah.
from ni equal 1 to something. You can write that state with sum of lambda.
Yeah, but this again, in that case, I was talking about many particles, many particle state. Here, this is really a single particle state.
Okay, that is just one nk.
Right, and the lambda. Let me give you an example. What could be lambda? It can be a wave vector, a spin, okay, or a polarization mode. It can be the index n of the harmonic oscillator.
It's just something that
That is just the eigenstate of some single
parameter
particle
of the
Hamiltonian.
energy.
Okay, so if the Hamiltonian H naught is just kinetic energy, then usually lambda will be wave numbers. If H naught is the harmonic oscillator, then lambdas will be the ends of the harmonic oscillator, single particle, don't confuse, okay? But it doesn't matter, okay? But that's what it is, okay? Actually, it can also be a lattice index. If you have a crystal, an ordered crystal, and you think of electrons in a crystal, also the site index is also a quantum number. Okay, and you can write everything in this basis. And we'll see in the next lectures which basis we choose for which problem, but that's the definition of lambda. And now we can also define a wave function. A phi lambda of R is going to be the space representation of the states lambda, or if you like, formally you define it as the overlap of lambda with the state R. Okay, it's the space projection of phi, so it's a function of space.
What is that? Phi?
Phi, yeah.
Okay.
Or you can call it psi, but let's call it phi. So phi is phi of lambda is some function of R, okay? And that's useful if you write H naught as a differential equation. Sometimes it's useful to write it in this way. But that's for one particle, okay? And for one particle, we know how to do quantum mechanics. We know that the wave function absolute value square describes the probability to find the particle at position R. You can calculate expectation values of various operators with this wave function. Okay, we know how to work with it. And whenever we're given a Hamiltonian with some potential, the first problem we want to do is to solve the Schrödinger equation, namely to solve such an equation. And we can do it more or less easily for one particle. But now let's assume that we have two particles in the same state. Let's take, for example, the helium atom as opposed to the hydrogen atom. Okay, hydrogen atom is described by a central potential, and the helium, if you ignore the interaction between electrons, and of course you are not allowed to ignore it, but let's put it aside for the moment, assuming just that you take into account the same potential given by the central potential of the ion, okay, then the Hamiltonian of helium atom would be similar to that of the hydrogen, but we have to accommodate two electrons and they are fermions, and they obey the Pauli exclusion. So what is going to be let me write now a wave function, lambda 1, lambda 2 of R1, R2, the wave function of two identical particles that occupy the states lambda R, lambda 2. Okay? So how do you write it for two particles? And R1, R2 are just names for the coordinates of the particles. So, in fact, what you have is the following expression. You can put particle lambda 1 in R1 and
just some summation on I and j of lambda I rj.
Yeah, but here we have, let's say we just have two quantum numbers, lambda 1 and lambda 2, but I can put the two electrons either in 1 and 2 or in 2 and 1, okay? But then it's of course, I'm allowed to switch them because they are identical. But now I have either a minus or a plus of phi lambda 1 R2, or maybe, yeah, just for aesthetics, although it's the same, let me write it phi lambda 2 R1, phi lambda 1 R2. So that's what I get when I exchange the particles. And I get minus sign if they are fermions, and plus if they are bosons. Right? This you know, I hope. Okay, so explicitly. Okay. Okay, good. So that's how it looks for two particles. What do I get if I have three particles? Then I have more options, right? Because I have certain permutations I can make on the particles and states, and all of them are identical, but I have minus or plus signs depending on the parity of the permutation. And in fact, if I want to write a most general wave function of n particles, okay, capital N, where n is a big number. Actually, even for two particles, okay, solving the problem or solving the Schrödinger equation already becomes a little complicated because you have to keep track of many terms, right? And if you have three particles, there are more of them, and it's exponentially growing, right?
More than that.
So, yeah?
More than exponential.
Yeah, more than, yeah, that's right. More
Factorial.
Than, it's like a factorial, exactly.
Yeah, because the number of permutations.
Right, so in fact, if I want to write, let me write it like this, where I goes from 1 to n, and n is a very large number, okay? But even if it's not so large, it's complicated. Then I get, there is some normalization factor. I'm not writing it, but it has 1 over some factorials, etc. Times what you have here is a sum over permutations. It's a sum over permutations of, let me now introduce a factor that I call zeta. I will define it in a minute. But you have something like that. So zeta is, let me define it here, because we are going to use it all over the place in the next few lectures. It's plus for bosons, minus for fermions. Okay? So if you want to write expressions that are good also for both types, you can always use this factor. Now, 1 minus sine p, and then you have here a p of lambda 1 r1 and times phi p of lambda 2 at r2 times until you get to rn, and that's p of lambda n. Okay? That's what you get. And I have a sum of many terms. Now, why is this factor? Let's understand it. So the sign of a permutation, I hope you saw it, the sign of a permutation is
when you write it in pairs, multiplication of pairs is how many pairs?
Yeah, it's how many exchanges of two you make. Okay, when you make any permutation, can be written as a product of what do you call it? I lost the word. Transposition. It's a. Yeah, החלפת זוגות. How do you say it in English?
Permutation.
Pair exchange. Okay. So any permutation is a product of exchanges of pairs, and if there is an odd number, that's an odd permutation. If it's even, it's an even. So the sign is plus or minus depending on how many permutations. And if it's negative, okay, then you get here 2 over 2, which is 1. Okay, so you get a factor of zeta. And the zeta is either minus or plus, depending on fermions and bosons. But if the permutation is positive, it doesn't matter because it gives you 0. Okay, zeta to the 0. Okay? So, altogether, if I open this sum, you get an expression of the size of the universe, okay? If n is Avogadro number, or even much less, much before, okay?
Then to write it as an integral or something.
No, so it's worse.
If it's a Avogadro number, I can...
But you cannot, that's the point, you cannot write it as an integral, right? Because of these alternating signs. You cannot. It's really important to keep track of the parity of permutations. Okay? Now this is horrendous. No. But let's discuss it when we get to the path integral. No, I mean, actually, we'll see later when we get to the path integral formalism that when you want to do it for fermions, it gives troubles. You have to know how to deal with it, okay? But let's not talk about things we didn't define, okay? Okay, so we are of course not going to work with this. It is just to give you motivation why we need a different language. I think we are all convinced by now. And there is a reason that we can actually be satisfied with a new language that I'm now going to define more generally as second quantization. Second quantization, why is it called second quantization? For some historical reasons. It's a way to reformulate quantum mechanics in a language that is exactly suitable for dealing with such cases, with many body identical particles. Okay? And basically the idea is that we're going to replace wave functions and Schrödinger equations by algebra. By algebra of some operators, and the building blocks of our theory are going to be annihilation and creation operators of particles. Okay, now let me explain why, by writing the general many-body wave function in the first quantization language, you have here too much information. You have too much information. That's why you can adopt a new language. Why you have too much information? Let's ask ourselves, what is the information we need to define a many-body state of identical particles? We know that exchanging the particles doesn't change anything, right? Because they are identical. So we need to, the following information is what you need to have in your arbitrary quantum state. You need to know first the quantum numbers. So these are going to be the lambda of single particle states. And the lambdas are, it doesn't matter what they are, but there better be something that spans all the Hilbert space of single particle states. And they define some spectrum, okay, because you can relate them to a spectrum of energies, for example, and the energies are denoted epsilon of lambda. These are single particle states, okay? Now, what can you do with identical particles when you throw them into a Hamiltonian that has these quantum numbers? You can start occupying states, right? And the state is completely defined if you just tell me how many you put in each lambda. That's all the information I need, right? Within the state, if I put 3 fermions, 3 electrons, let's say, and they're identical particles, I don't know which is which, right? I just know that I have a state lambda 1 with 3 electrons, and lambda 2 with 17 electrons, and so on and so forth, okay? So we only need to know the quantum numbers, and we need to know occupations n lambda for each lambda. And if we know all the occupations of all the lambdas, and lambda is a complete set, then we know the state. And a general state in the basis of our Hilbert space is just going to be something like that, lambda n1 and lambda 2. Okay? Where n lambda I is larger or equal to 0 and integer. Okay? And specifying all the occupations of all the lambdas is completely defining the state. Okay? I don't need to know anything more than that. Okay? And then, of course, I need to be able to describe operators for which I know how to compute the expectation values of such states. So if my Hilbert space is going to be spanned by these states, then I have to be able to write a matrix element of any operator in this basis, I can write expectation values. So I need to have some building blocks which allow me to write all the states and all the operators. And then I'm done. Okay, I have a complete description of the problem. Whether I know how to diagonalize the Hamiltonian is a different issue. Maybe that's difficult. But let's first adapt a language where we can write it down. When you can write something down, then you can start developing techniques of how to solve it. Okay? So what are going to be our building blocks?
But if you know all the eigenvalues, that means
No, so these eigenvalues, we have to
all
be
the
careful.
eigenstates, you know how to diagonalize the Hamiltonian.
No, I don't know so I don't know the eigenstates. The eigenstates, okay, so let me be a little more careful. What I wrote here is just the Hilbert space is spanned by all these states, okay? They're all the states of this form, and I'm going to give it a name. If I sum over all the lambdas and all the n i's, this is called Fock space. Okay? It's a Hilbert space of many body states of some kind of identical particles. And yeah, and a general many body state, psi. How can I write it? The most general. I don't know if it's an eigenvalue of anything.
On all n lambda I.
Exactly. So exactly. So the most general wave function is
coefficient that depends on all n lambda i's.
Exactly. Right.
Times the nasty state.
Right. So that's exactly right. So I have to sum over all the possible choices. Now, just for compactness of notations, let me denote, instead of writing n of lambda of I, let me just write it as ni. Okay? Let's just agree on that. Okay? So I just count
There is a morphism there.
Yeah, okay? So I'm summing over all possible choices of the ni's of the states with some coefficients. Okay? Now, when I'm writing this, what I mean by it is that the occupation N1 is anything between, I'm summing over all possibilities for choosing it from 0 to infinity, and and N2 goes from 0 to infinity, and
you can't use Einstein notation for infinite space.
I don't know. What is it? Anyway,
It will be convenient.
But this is what I mean when I just write it like this, right? This state, by the way, also doesn't have any limit on the number, the total number of particles. But suppose I want to write down a wave function that has capital N particles. How do I write it?
It will be just summing on all possible states on a simplex.
Yeah, so again, it will have this form, but if the total number of particles is capital N, there is a constraint on the ni's. That's all. Okay? Right?
Summing on a simplex, right?
Yeah, so I can write it actually like this. writing the sum over all possible ni's, except under the conditions that the sum over all i's of ni will give n. Okay? And then, under this constraint, I still have, sorry, I have some...
It's the volume of n minus 1 dimension simplex, right?
If you want to call it this way, I have to confess that I don't know what you mean. But that's just a formal definition, okay? Okay. All right, so in fact, notice that the state of this form, which has no constraint on the total number of particles, is in fact generally a superposition of states with different numbers of particles, and that's fine too. Okay, that's well defined. In many body systems, we can have such states. We'll see later in the course that we need them in the case of superconductivity, for example. Okay? But it's a well-defined way to write any state. And then with this state, we may want to calculate expectation values of operators. But the nice thing about the second quantization language that I'm now defining is that both the states and the operators of any kind can be expressed in terms of simple building blocks. What are the building blocks? They're going to be annihilation and creation operators. Okay? And we'll first have to define them. So we already defined them for very specific problems where we could relate them to something we already know, like coordinate and momentum. In general, you don't have that. But you can define them in such a way that you can start from some vacuum. Okay? So that's the core of the formalism. You have a vacuum state denoted by 0, and the definition of the vacuum state is not unique. It depends on the problem you want to describe. Okay? But for a given problem, you always want to define a vacuum state, which is the one that is completely empty of all particles.
So it is unique because...
No, because we'll see later that sometimes you can take something that is already full, like for example, you already know that for fermions, what is the ground state of many fermions? They cannot all go to the ground state, right? What is the ground state? At 0 temperature, what will be the state of many fermions? You know it from statistical physics or from solid state. You occupy all states up to the Fermi level, right? So it's, in other words, it's the Fermi C, right? So sometimes you want to view the Fermi C as a vacuum. And only excitations above this are the particles. And there are many such examples, but that's a very canonical one. Okay?
Why?
We'll see later, okay? It's a matter of what is useful, okay? And but you can also have...
If you will use the annihilation operator on the vacuum, you're supposed to get...
It depends how do you define your annihilation. So that's exactly the thing. So what you want to have, let me tell you what is the formalism, and then we'll see many examples where you can apply it in different manners. Okay? So you have a vacuum, and then you have lambda. These are the quantum numbers. And for each lambda, you can define, and we will define it systematically. You can define annihilation and creation operators in such a way that A lambda acting on the vacuum will give you 0, and A lambda dagger acting on the vacuum, what will it give? Just single particle at the state lambda, which is what we called before. Okay? And then there are a set of algebra rules. So we have to know there are some algebra rules, commutators. And that's it. These are the building blocks. Okay? And once you have that, you can express every wave function and every operators in terms of combinations of A's and H daggers, and you can compute matrix elements and so on. Yes?
What will be the result if you apply the dagger operator A and the dagger twice?
Okay, so you're getting here. So I told you what we want. Now we see how we do it. Yes.
So
yeah.
in first quantization, we applied the operators on the wave function, and now we always apply it on the vacuum. There is no point in applying it on the wave function.
In first quantization, you express everything explicitly in terms of wave functions. Okay. Now here you also have. I mean, these guys are also. This is also a wave function. It's a many-body wave function. But you don't want to write it as a wave function. You want to write it as a product of creation operators acting on the vacuum. Okay? Mm-hmm. And then it's well defined. And then eventually, if you also write operators as combinations of A's and A daggers, then the calculation you have to do for any matrix element is calculating expectation values of some combinations of A and A dagger in the vacuum. Okay? And then I'll show you the rules how to do. Okay? But yeah, basically, so it compactifies everything. And the fact that you have this, that you have either, and here the commutators, well, I'm going to show you, depend on whether you are fermions or bosons. It depends on the statistics, okay? And the statistics will be embedded in the algebra rules of the operators. So you don't have to keep track of pluses and minuses. You just have to know, I give you fermions, it's this, I give you bosons, it's this, and just stick to the rules. Okay?
No combinations of functions. No combinations of...
Yeah, so in fact, the more advanced stages, you can make composites of bosons and fermions, you can convert bosons to fermions, you can do all sorts of tricks. First, and that you may need to do if you want to solve some complicated problem with interactions, but first we want to get familiar with the building blocks, okay? So let's go to business. So I'm going now to introduce the formalism that I call the second quantization, and I already told you that for any type of particles, and we have only two classes, fermions and bosons, at least in the elementary particle worlds that we're familiar with, we want to have a set of rules and building blocks to describe any physical problem. And the first thing we want to do is to define a creation operator. Okay, so this is
generalize the definition.
Yeah, we want to generalize the definition, and to make it such that it will apply to both fermions and bosons.
So we're a mathematician today.
And I'm going to use this notation zeta, which the convention is that it's plus for bosons and minus for fermions. Okay? So we already know what is our Hilbert space. The Hilbert space is a set of states, or at least this is the basis of the Hilbert space. It's a set of states that are spanned by states with well-defined occupation of all the possible single particle quantum numbers in the system. And because this is the basis of the Hilbert space, then if we want to define an operator, we have to know what it does when it is applied on an arbitrary state in our basis. Okay? Once we have that, we can compute matrix elements and expectation values of the operators, if there are any. Now, I also want to mention, although it is clear, this is an orthonormal basis. So if I take a state with some occupation and I compute its inner product with another state, what is this going to be?
Delta of n.
Yeah,
One,
exactly. It's going to be
n1,
delta
n2 tag n2, and so
exactly. Okay. So two states with different occupations in even one of the slots is are orthogonal. Okay, and if they are the same, then it's one. Okay.
We are not speaking specifically about independent work. Yes, they can interact with each other.
They can do whatever they want. This information is in the Hamiltonian.
Yeah.
Okay. Now we're talking about how we describe a particle. Okay. Okay. So it's really a definition of how we formulate the state with a given number of particles. Okay, so this is going to be the definition of a creation operator that we'll use, and for any index I is one of the quantum numbers, lambda I. If I apply it on a state where I have some occupations, and in particular in the slot I have Ni, okay, Ni particles in slot I. So the index I is some index that hierarchically defines my quantum numbers. Okay, how you define the hierarchy is a matter of choice. For example, it's according to energies, or if you have lattice sites, you can just go by the lattice size, it doesn't matter.
But then you will have.
You have to define it. No, you can define it to be. It doesn't matter. Okay, but you can define some ordering. But in the ith slot, I have ni, and I apply on it the creation operator.
You
then
add a particle.
This is a definition. Then what I get is something that I will define in a minute. Ni plus 1, let me just put in a minute. Okay, zeta si. I'm owing you a definition of these things, but it's some number times.
Spin is the number of symmetry in the system.
No, don't guess. I will define it. So essentially up to a numerical factor that I still have to define, what a dagger I does is to add one particle to the slot I. Okay? So this is a definition of a creation operator. Okay? So the resulting state is this, and there is, however, some numbers that if you want to define the new state with more particles in terms of the older one, you may have to use, this will give some normalization factor, okay? You can worry about it later, but this is a definition. Now, what are these objects? And notice that here I introduced the zeta in order to account for the possibility that there are also fermions.
You have also zeta as an index?
Yes. Zeta is an index plus or minus for bosons. Okay, that's the convention.
The slot must account for energy levels?
For example, doesn't have to be. I said it. You could choose a different way.
How can you then define the addition of a particle to a slot?
Okay, let's not call it a slot. It's a quantum number. Okay, you take all your quantum numbers. It can be on a grid, like for example k vectors on a grid, right? And just don't call it a slot. Okay. So if I'm applying, let's say that it's k vectors, like in the case of the phonons or photons, then I apply a dagger of some k. What it does, it adds a photon to this k, this particular k. Okay? So I'm just writing it like this so that we'll know what I'm talking about. Okay? So what I mean is that actually Ni is increased by 1, but all the others remain the same. All right? Okay, now let me define what is this factor of Ni plus 1. What is the index zeta doing here? First of all, if zeta is plus, we have bosons. For bosons, you already know, you are already familiar with this, right? Because this is just the square root of n plus 1, just the square root of Ni plus 1. But for fermions, it's meaningless to have such a thing, because fermions, you cannot occupy more than one, in the same quantum number, right? So for fermions, Ni can never be larger than 1. It can be 0 or 1. Okay? How do I take it into account? I want to define this such that for zeta equal plus, it's just the number plus 1, but if zeta is minus, then it's Ni plus 1 mod 2. Okay? And I don't actually need the 1/2 power because it doesn't matter.
Yeah,
it's square root of 1. Okay, so this is either, so you see this is either 0 or 1, right? And actually let me show you how it works. Maybe before that I also owe you a definition of SI.
Number of symmetries?
No.
No.
So it is. Yeah?
If you apply on a state it's already occupied, you just zero. And you
Yes,
zero,
and let me show you how it is. So if for example this state, let me first do it just that you feel satisfied with the definition. If ni here was 0, okay, then I apply a dagger, I get 0 plus 1 modulo 2 is still 1. So I get 1. This gives me 1, and here I get 1, right? But if ni was 1, ni plus 1 will give me 0, because it's modulo 2. And therefore what I get is 0. So if I apply, in other words, if I apply AI for fermions, okay, AI acting on blah 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 0.
With 0 you mean vacuum?
No, it's not a
With
vacuum.
0.
This can be something.
No. I mean when it's equal to 0, because you have a coefficient of 0.
It's not a vacuum. It's 0. The number 0. It's annihilated. Okay. So
Yeah,
let me write it down and then explain. So if I start with a state that has the ith quantum number is empty, I apply a dagger, I get here I will get minus 1 to the s, which I still didn't define. So times I will get some number times, which is just a phase factor or plus or minus, because s is a number, and then here I get 1. Okay, this is 1. However, if I apply it on a state that is already occupied, I get 0. Okay?
yes,
Just 0.
But
Okay? So it's destroying it. It's annihilating. It becomes an annihilation operator. Yes?
אבל האפס פה הוא וקטור, כאילו, זה לא אפס סקלר.
No, it's...
התמונה של זה וקטור, זה סטייט.
It's 0. It means that this state disappeared. Okay? If you apply this on some superposition of states, this contribution will disappear for your sum. Okay?
That is...
You're right. Yes. If you like, it's the 0 vector, but it's a vector times 0 is 0. Okay?
Okay.
It's just 0. It's the real 0, not...
Yeah, vacuum is something that...
No, a vacuum is a state. A vacuum is a state. A vacuum is a state. It's like the ground state.
Yes.
Okay?
When there is no particles, that is just the 0 vector.
Right. If you apply the annihilation operator of any quantum number on the vacuum, and it does it, it's the same for bosons and fermions, you get 0, right? Mm-hmm. And you can explicitly see it also in the harmonic oscillator. It's an operator that if you apply on the ground state, it gives you a 0. It's a 0 eigenvalue. Okay. So this is what you get for fermions, and that's why the definition. Now, what is S? SI is okay, sorry, mj. And you see, this is why formally, in order to work with this definition, you want to define some hierarchy. Okay? How you do it? It's arbitrary. Actually, this definition is also kind of arbitrary because eventually what it gives you is a phase factor. Okay? It gives you either minus or plus because if zeta is minus, if zeta is plus, it actually doesn't matter. It's just 1. If zeta is minus, then depending on the parity, so what is the meaning of this SI? It counts, imagine that you are ordering the quantum numbers or the slots or whatever you want to call them on a chain, and you are counting how many particles occupy the states up to one before your state I. Okay? And then you count the number, and if this number is odd or even, the phase factor will be plus or minus or plus. Okay?
That works. Or
now, why is it kind of arbitrary? Because you know that phase factors in wave functions generally don't have direct physical meaning. What does have physical meaning? Only differences. Okay? So whatever is the definition, only if you calculate something measurable like the overlap of two states or a matrix element of operators, the phase factors or differences between them will give you some, or might give you some phase factor, okay? But as it is just a phase, yes?
זה יהיה אפשרי גם לקחת את זה כאילו 100 פלוס 1 ומעלה? זה כאילו...
Yes, as I said, it's arbitrary.
זה יהיה...
It's arbitrary.
Okay.
Okay, also the ordering is arbitrary, right?
Is there like an intuitive way that we can understand why it's there?
No, it's not intuitive. It's technical. It's a trick that gives you at the end. It gives you for any physical quantity. It gives you the right thing. Okay, it works. It's a trick that works.
It works for
nothing
and
else.
for bosons we
Yeah.
don't care.
By the way, we call it a string because it's like you are defining a state in a very non-local way in a sense, because to some extent this phase factor knows about the number of the occupation of other states, right? You are describing, so it's not local. It knows about occupation of many states.
You can extract from that dynamics.
No, you cannot. It doesn't have.
So it's not an interaction.
No, but as I said, when you have differences of such phase factors, it may play an important role. Okay?
Okay.
And in fact, you are going to see, I think in one of your tutorials, you're going to see how you map some kind of operators to fermion operators, and this takes care of the correct commutators. Okay, for example, you can map spin operators to fermions or bosons. And we want to keep track of
That is just someone did the mathematics and calculate that. And
yes.
They want us to make sure that's compatible with what we're using.
Right.
Okay.
Okay, so it's compatible, exactly. Okay, so that's a definition, and because of that, you know that if you start from a state that is completely empty, the vacuum, which is 0, 0, 0, 0, you apply AI dagger, what do you get? I get that everything is 0 except I have 1 in state I. And then I apply AJ dagger, I get 1 in AJ. And if I apply AI dagger twice, and these are bosons, not fermions, then I get 2. And this way, I can in fact get all the states in my Hilbert space, right? I can get all of them.
Wait, if
so
you apply again
if I apply
on a fermion, you will get 0.
Yes, if you apply on a fermion, I get 0. But if but still the statement is correct. But I can get any fermionic state, any legitimate fermionic state, which is 0, zeros and 1s, by applying some number of A daggers, and I can recover the entire Hilbert space. That's the point. Okay. So
that means
so in fact
A dagger cubed for fermions is just the identity.
No, it's actually 0. Because
no,
it's 0.
Cube.
It's 0.
Cube, it means you.
Because it's something acting on
yes. Okay, it will
okay.
be the total. Okay, it's not just okay.
In fact, we already have one identity that we have to keep in mind for fermions. AI dagger square. Okay. This is an operator that annihilates any state in our Hilbert space. Therefore, by definition, it is the 0. It's the how do you call it? Identically 0 operator.
That means all eigenvalues of the for fermions, all eigenvalues are 0.
Yes, this operator is the 0 operator. Mm-hmm. Yes. Okay. Okay. So the conclusion from here is that if I take the vacuum, I can get any state N1, N2, N3. Any state can be written as a product of all the possible indices of, and there will be a normalization factor that is just ni factorial square root times A dagger I acting on the vacuum. Okay, so I already have something that allows me to define all the states by just application of A daggers. Okay, and of course, in the case of fermions, Ni can be only 1, at most 1. Okay. All right. So now, however, you already, I think, asked about it before. Here I defined AI dagger, and I also want to see what happens if I apply AI dagger and then AJ dagger. Okay, I have two different quantum numbers, and I want to apply the creation operator one by one. But now I'm going to show you. Actually, I'm not going to do the details. You'll do it in the tutorial, but the order of application of A daggers matter. Okay? Why? They are not necessarily commuting. Yeah?
the annihilation and creation operator, for example, in harmonic oscillator, are diagonalizable. Not orthogonally diagonalizable, but they are diagonalizable, right?
What do you mean? Sorry.
In harmonic oscillator,
yeah.
the annihilation and creation operator are diagonalizable, right?
I don't know what you mean by they actually they actually don't have expectation. Okay, they don't have expectation value in any state. In a state with well-defined number of particles.
It's combination of states that they can maybe get.
What is diagonalized in the harmonic oscillator is the combination A dagger A.
Yes, but.
Okay, we'll get to it. This is actually.
Can be, okay.
I can show you.
Okay, actually, by using this definition, what one can also explicitly show that it gives the number operator. But let's not jump ahead. Okay, let me first do what I plan to do because it's important for our theory to our formalism to be constructed systematically. So if I take again an arbitrary state and I apply on it AJ dagger and then AI dagger, and let us consider the case that I is different from J. Okay, and what do I get? I'm not proving it, so I leave it to the tutorial. But when you do the algebra, you're going to find that this gives you zeta times the state that you get by applying AJ and AI in the opposite, in the reverse order. So if you exchange the order, you pick a factor of zeta.
Because modulo 1 and 2.
That's because the size.
The definition of A is exactly the same, just -1 in the manner of Z.
No, absolutely not. So actually, we don't have a free. Once we define, this is a very important question. Once we define the A dagger, this is a definition. We no longer have the freedom how to define A. Okay, and I'll actually show you next what it is. Okay. That will be our next stage. But yeah, it actually will follow. Okay? But let's just work with the A daggers first. So you can show by simple algebra that this identity is obeyed for any state and for any I different from J. Okay? Now let's just, so you see it's these and these are the same state. So I can move this vector to the other side. And then I get that A dagger, AJ dagger minus zeta, AJ dagger, AI dagger acting on any state is 0.
So
Okay?
you choose a base and then because of that it's...
So because of that, anything that acting on any state gives you 0 is the identically 0 operator. So this is 0. Okay. And And now let us see what it means for bosons or fermions, because remember, zeta is plus or minus 1. So, for bosons, we get that AI dagger AJ dagger minus AJ dagger AI dagger is 0.
For bosons, they are commuting.
What is this?
Fermions.
This is commutator, that's right. So
And
AI
for-
dagger,
And for fermions, they are anti-commuting.
exactly, that's right. For fermions,
So we write it with curly brackets.
we get that AI dagger AJ dagger plus AJ dagger AI dagger equals 0, and this object is called an anti-commutator. Okay?
Excuse me, Pat?
Yes?
Or maybe I just lost you there, but can you explain, please, the middle equation, the main equation? Why?
This one, why is this correct?
Yes.
You will do it in the tutorial.
Ah, okay.
Or in the homework. Or both.
Okay.
Okay? So here I owe you a proof, but it is just application of the algebra, that's all. And by the way, notice that indeed we define here this exotic string, but actually for our purposes you just get the factor of zeta. Okay, so these are the algebra rules, and you see that they are really embedded in the definition of the operators. Okay, so the operators for fermion, although we denote them maybe by the same letters, they don't have the same algebra rules. I have to tell you if it's a boson of fermion. Okay? There is also a notation if you want to write this commutator more generally. Let me write here a definition. Sometimes you will see in the literature that you define it as a commutator with an index zeta, where once again the meaning of this notation is that if zeta is plus is the commutator, and if zeta is minus, it's the anti-commutator for any A and B. Okay? That's just a definition. But I don't know, sometimes I think these are more common, just to use, you know, you either talk about fermions or bosons and try not to get confused. Okay? All right, so, okay, so we proved, we already proved a very important algebra rule. Although we still don't know exactly what is the annihilation operator, we do know that actually its definition is the conjugate, the dagger of A dagger, right? So if you just define AI to be the dagger of AI dagger, then if AI and AJ dagger commute, also AI and AJ will commute, right? This is trivial. And this is all for I different from J. Now what happens if I equals J? So wait, now it depends again if it's bosons or fermions. If I equals J, let me erase this. if I equals J, for bosons, AI equals 0. Why? Because the operator commutes with itself. It's trivial, right? So for bosons, it's really trivial. What happens for fermions? For zeta equal minus. So we want to ask what is
But you said that A square is not defined.
what?
You said that A square is not defined, so how is it
No, it's
calculated?
not. It's not that it's not defined. It's okay. Let me write it down. So let us ask ourselves, what is this? Okay. I'm claiming that it's 0, but why is it 0? Not because of the same reason.
Because it's made.
Because it's just look at the definition. It's AI dagger square plus the same thing. But these are 0. This is the identically 0. So it's also 0, right? So therefore, these commutators that I wrote here are not only for I different from J, it's for any I and J. Okay? And I can leave them like this, and this is one algebra rule that we already proved. And we are missing one more, so there is another trivially following rule that if we eliminate the dagger on both of them, we also get the same thing, right? Because it's the dagger of this equation is that AI, AJ commutator give you 0. Okay? All right. Now we are missing a very important building block, and that's the commutator or anti-commutator of A and A dagger, right? Which for bosons we actually already know. We know from the example of the photons and phonons. But now it comes the time to, yeah?
Is it makes sense to talk about the מצב הקוהרנטי של פרמיון, binary state? Because if I'm applying a dagger on some
So we will talk about it much later in the course.
Okay, it gets
When
like
we
H
get to
squared
the
gets
path
0.
integral, because coherent state is an eigenstate of the annihilation operator. But we are not there yet, okay? We are still defining our building blocks. Then we'll build the tower, okay? And then we'll see how to destroy the tower, okay? All right. Okay, so now comes the time to see what, just like what we did for the creation operator, I want to see if I take an arbitrary state, what do I get if I apply annihilation operator? And I'm claiming that actually it already follows from the definition, but we have to work it out. Okay, so okay, so let us take this definition, and also let us keep in mind the orthonormality of our basis, because now we are going to use it. I can take this this expression and I can put a dagger on both sides. Okay, I look at the Hermitian conjugate of this equation. In the left-hand side, I'm going to get, if this was a bra, I'm going to get the cat state of the same thing, okay? And let's put here an I, okay? And acting from the right with the operator AI, which is, as I said, AI is the dagger of AI dagger.
Now you can just multiply on the right side.
Wait. So this is the left-hand side. On the right-hand side, what do I get? The factor here is just a number. So it just stays, it's a real number, right? So it just stays the same. Zeta to the SI. And this simply becomes state, blah, 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 and Ni plus 1. Okay?
Now you can multiply by the cat.
Right, so that's exactly, that
For
will be my
general
next
stage.
stage. My next stage is going to be to look for a matrix element, okay? So, but before I do it, just for convenience, you agree that this equation will still be correct if I put primes on all of these, right?
Sure.
Okay, it's just a notation. Okay, for convenience, let us look at this, and therefore I know that now I want to sandwich. This is a cat state. I want to sandwich it with a brass state, and the brass state will be N1, N1, 2, etc. without the primes, okay? So, it's a matrix element between a state with primes and some arbitrary state with Ni.
You forgot the I in
Well,
the I.
yes, that's right, thanks. Okay, so I want to compute, it, but actually I know how to compute it because this guy, I already found that it's some number times a cat state. Right? So let's use it. And I'm taking the number out, and I prime plus 1 zeta to the Si prime. And then I have N1 prime, N2 prime, blah, 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 but Ni prime plus 1. And I sandwich it with N1, N2, Ni. Okay? Clear? So again, what I did, I first computed this object and denote it as just a state, but the conjugate of the state with Ni prime plus 1 particles in the I slot and times a number. And the sandwich with another state gave me an inner product that I can compute from here. What is it?
Just the delta, but the interesting stuff happened at the
Right.
slot when it's delta of Ni tag plus 1 Ni.
Exactly. So this is a
Like in
delta
all
of
harmonic oscillators.
right. So it's N2 prime, blah, blah. but there's one in the ith slot. I have a delta of ni and ni prime plus 1. Okay? And, okay. Alright.
And you have more deltas
So,
from I to and so
therefore, yeah, and therefore,
you have after ni more.
let me rewrite this state. So let me rewrite this state in terms of the using this delta, right? So the delta tells me that everywhere where I had ni prime plus 1 should be ni, right? So in other words, I can replace this by ni of to the power half, okay, ni zeta. I have zeta to the power s, it's wait, let me just think for a minute. Yeah, it's so it's not si because yeah, sorry, it's actually si. Yeah, it's si because the s, okay, s, let me just remind you the definition. Exactly, it's sum of j up to I minus 1. So it doesn't depend, it depends only on the occupations of the other things which we didn't change. So it's exactly the same, okay? And from this, I can actually extract, I can go back to my equation here, okay? So remember, what we saw here is that we could write the conjugate of AI acting on the state gives me the state with the primes. Wait, sorry, I'm confused now with something. Yeah, okay, let me go one more step. Okay, so getting out of one, so yeah. Okay, so we know what this is, but I want to use here one more identity. Okay, what we have here is an overlap of ni prime, ni prime, with the state which is AI acting on the state without the prime. Okay? Right? We can rewrite it in this way. We can view it, originally we got it by conjugating what a dagger does, but we can view it as AI acting on something overlapped with the one with the prime. Right? But now, and this we know has to equal this deltas, product of deltas times a number. Okay? But now we also know that in this number I have So it needs to be something that if I act on it with or if I overlap with this, will give me the same thing. Okay? So you can easily convince yourself, I think, that it works if I'm writing the following identity. I'll erase this now. AI acting on N1 and 2, Ni equals this number, which is Ni to the power of half, and actually, do we need the index zeta? I don't think so, actually, because if it was 0, it will not. I mean, you actually don't need to keep track of it, but let's leave it. Okay, and then we have a zeta to the Si, and then what we have here is something that will give you this kind of delta function with the state, with the primes. Okay?
Why you switch Si prime and Si?
Because we just said it's the same. They are just
because
the same.
the deltas before that are the same.
Yes.
Right.
Si equals Si prime. Okay? Okay? So, yeah, we just did it, but I erased. Okay? So, right, so the state with the primes is such that Ni prime has to be Ni minus 1. Right? And all the others are the same. Okay, so this is what it is. It's Ni minus 1. Okay. So this identity is consistent with either looking at it as a matrix element of AI sandwich between two states, or as the inner product between two states, this one and this one, provided that the state you obtain by applying AI is reducing the number of particles by 1 at the position I, and there is a prefactor which has Ni and not Ni plus 1. Okay? Okay, so we just derived what is A doing, and in fact, together they give you a concrete rule of what happens to any state if you apply A dagger, what happens to any state when you apply AI, and then you can play with applying one after another and see what you get. Okay?
The relation just follow.
Right, and let us now see, and again, I'm not going to do the details of the algebra, but you can already guess what kind of calculation I need to know in order to get the commutators of the algebra rules of A and A dagger. I can look at this state and apply on this AJ dagger.
You can just put dagger on that equation and find the real.
No, that will give me this will give me AI AJ equals 0, which, yes, you're right.
No, what I'm saying is applying it on both sides, and then you know what is the dagger of multiplication.
No, from this you don't have any information, okay? This follows from... This only gives
What
you...
is the dagger of multiplication of operators?
I think this you know. Okay. This you should know.
Yes, it's B dagger, A dagger.
Right. Okay.
So
Okay.
from
So
that
you're
I
right.
get the relation of the commutators on
No.
the
No.
לא, אתם לא רוצים אותו דבר, היא רוצה A דגל, לא AA.
You know, you don't even need this in order to show that if AJ commutes with AI dagger, then their conjugates also, right?
Yeah. Okay.
We want A.
But that's not what we want. I agree. You're right. You're right. This is
okay.
correct. This is correct, but I'm claiming it's not really a new. It's not really a new relation. Okay, and it's true, by the way, also for fermions, of course. Okay. No, that's true. This is part of the algebra, but we are missing one building block. It's the commutator or anti-commutator of AI and AJ dagger.
Oh.
Okay? And in order to do that, you need both. You need both. But now we have them. So you can apply, take this and apply AJ dagger, and you can reverse the order. In both cases, you will get to the same state times some number. And if you do the algebra carefully, what you're going to find and I think you will get it in the homework, the next one, and just do it yourself. So again, the trick will be that you are going to get the AI AJ dagger acting on some arbitrary Fock state equals this is for sorry, let me just check something. Yeah, so if I is different from J, you're going again to get zeta times this operate the opposite direction times the same state. And if you transfer the right hand side to the left, you're going to get that AI AJ dagger commutator or anti-commutator is 0. This is for I different from J. But you can also do it from I equal to J. And then what you're going to get is you're going to get 1. Okay? So the result will be, let me just state the result for fermions. So let's do first for bosons for good measure. This equals delta of I and J for fermions. AI AJ dagger is again a delta. Okay? And the first rule you already know from our experience with the phonons and photons, etc. This is sort of new, but the set of rules is actually, so let me maybe summarize them. So here. Okay, so these are the bosons. Order the same. 0. AJ dagger is 1, so delta. For fermions, everything is the same, except you replace the commutator by an anti-commutator. Okay. AI, AJ dagger is delta AJ. Okay. So this is it. These are your building blocks. We already saw that any state can be represented as application of some power of A daggers on the vacuum. And now, using these algebra rules, we can shift things around, right? Because, for example, let us make a very simple exercise. Just put this in a box, okay? So these are the algebra rules. You also know that, now I can erase this. You also know that AI acting on the vacuum, what it will give you? 0 for any I, and therefore, let us now make an exercise. What happens if I apply AI dagger AI on the vacuum? What do I get?
0.
Right? But on the other hand, if I apply it in the opposite order, what do I get?
The 0 vacuum.
Yes, I get back the vacuum. That's right. All right. And that's true for both fermions and bosons. So what have I done here? This is creating a particle, but then you annihilate it. Okay, and if you act with a different index, I get 0. Right? Okay. Now another exercise, which I think maybe you will.
The number.
You will also do it in the tutorial, but just the number operator exactly. So I'm again not doing any calculation here. I'm just
the difference of those. It's the commutator, actually, right?
Right. So if I'm so if I take
Something like that.
a state which has some ni at the state I, at the quantum number I, and I apply the operator A dagger AI on this. What do I get? Yes. What is the answer?
And
Ni times that state.
Right, exactly. It's Ni. So this is an eigenstate of this operator, which
Therefore, diagonal.
I'm going to call a number operator, and the result is going to be the number Ni. Here it's an eigenvalue already, and I just counts the number of particles, but only at the state, right? and it's the same state. So it's really this state with well-defined number of particles on state I is an eigenvector of this operator with eigenvalue and
it's diagonalizable.
So if you have a Hamiltonian that is just a sum over A dagger A, you can diagonalize it, and the result for the energy it will be just this number times an energy state. Okay, but if you have a Hamiltonian that that is not diagonal in this basis, or if you have interaction terms, and we'll get to this, you get something more complicated, but you can work it out using these algebra rules. You can move things around, okay? And the idea is if you are exchanging creation and annihilation so that the annihilation is on the right, then if you bring it to the vacuum, it's annihilated, okay? And then you are remained with only the things that you picked by doing these manipulations. We'll see how we use it in the future calculation. Okay, so there's just one thing I want to complete today, because I think we got to the main building blocks of our theory. Is you want to describe a system of some identical particles. You have to tell me first, bosons or fermions. Second, give me a set of quantum numbers, but they have to be such that they are a complete set. Define creation and annihilation. What?
I need to give you also the spectrum.
Not necessarily, depending on what you want, but I do want to have a set of, by saying spectrum, you already assume that there is some Hamiltonian that you diagonalize. I'm not sure there is one, okay? Or maybe it's not the one that I want to solve. But just to formulate the problem, I need to define a set of quantum numbers, a set of creation and annihilation operators with respect to these quantum numbers, and very, very important, I want a vacuum, and the vacuum is such that any annihilation operator annihilates it. So there is a package deal, a vacuum and the definition of an annihilation operator coming together, okay? For each vacuum, if you want to change the definition of the vacuum, you have to change the definition of the annihilation operator, such that this is what makes them annihilation operators, okay? So it's a relative to some definition of your vacuum, okay? Very important. Okay.
So how it's possible to, for example, have what you described before with the me energy level?
We'll get to it. We'll get to such examples, okay? This will be exactly one of the cases where we may want to define our vacuum differently, okay, for some purposes, okay? So we'll see several examples. Okay. So the one last thing I want to do for today is to consider change of basis. So I told you that to define your creation and annihilation operators, you always define them with some quantum number lambda. And lambda can be K vector, it can be latticite, it can be harmonic oscillator index, whatnot, okay? So some index, it can be spin, or some discrete degree of freedom. But suppose you have a problem where the Hamiltonian includes two terms one is easily described in one basis, and another is not so well described, or described better in another basis. So you want to have the freedom to switch from one basis to another, okay? And let us look for a prescription how to do it. There's a very simple transformation that allows you to switch. An example for a change of basis that you are already familiar from the field theories we discussed in the beginning is that if you have some theory in real space, it is written in terms of fields that are local in space, but in the Lagrangian or in the Hamiltonian you have terms that are gradients, then it's useful to go to Fourier space. Okay? So this is an example for a change of basis. Okay? So you can do the same with creation and annihilation operators. Suppose you have some quantum numbers lambda, and with respect to them, I can define annihilation and creation operators N and A dagger. And what it means is that if I take the vacuum and I apply A lambda dagger, I get a state with only one particle, and that particle is in the state lambda. Okay? Okay. Now, so I had the state that I called set of quantum numbers that I called lambda, or lambda states, and I want to switch to another quantum number that I call it mu, okay? For example, lambda can be R, and this can be K, okay? Space and momentum. But for the states lambda and mu, I don't want to transform from one basis to another, right?
Yeah.
Because you can always represent the state lambda. I can always represent as a sum over mu of, actually let me use here a projector operator mu times lambda, right? This is an identity. Why? Because the sum over mu
for momentum, we know what
of all the states, if mu is a complete set of states, this is the resolution of identity. Okay? You already seen it a lot. Now what is written here, if I just rewrite the expression, then the state lambda can be expressed as the sum over mu. Now, mu times lambda is a number, right? And
for momentum, we know what it is.
yeah, for the momentum, for example, it will be
That's
e to the ik, right? But that's right, exactly. I'll mention it soon. But generally, what I want to mention, it's a number. It's not an operator or something, right? It's just the overlap of these two states. It's well defined times mu. Okay, so here I have. So these guys, I can call them a coefficient C mu lambda or C lambda mu. It doesn't. Okay, it's a matter of definition, and I get an expansion with some coefficients in the new basis. Right? Now, using that, this is something you already saw in your undergraduate. I can easily convert the formulation to creation operators, because what is lambda and what are lambda and mu? They are nothing but application of the A dagger
It's like the
on lambda,
Lorentz matrix.
on the zero. What?
It's like the Lorentz matrix.
Yes. So right. So both states can be expressed as some creation operator acting on the vacuum. And therefore, if I plug in this identity here, so this I write as A lambda dagger acting on the vacuum, and this I write as A mu dagger acting on the vacuum. I'm getting an identity which I can forget about the vacuum and just express A lambda dagger as a sum over these coefficients times A mu dagger, right?
You want to write it with upper indices or something? So it will be actually summation.
No, I mean it's okay. You can write it any way you like. If I write it like this, it's definitely correct. Okay. Actually, let me be a little more. So, just for the conventional algebra, because I'm converting from mu to lambda, let me call it C lambda mu. Okay, but it's a definition. All right, so let me write down the results. So what I got here is that A lambda dagger can be written as a sum over mu of mu lambda. Okay, this is now it's an operator identity, and because of that, I can also write directly an equation for A lambda for the annihilation operator. Why? Because it's just the conjugate of the left-hand side. So A lambda is the sum over mu of the conjugate of what I wrote here. Exactly. So it's lambda mu, which is actually the complex conjugate of
C lambda mu.
Of if this I call the C lambda mu, then this will be C star lambda mu times A mu. Right? Okay, let's take an example which we already mentioned. The going from real space to Fourier space. So in the examples that we showed for the photons and the phonons, in both cases, we got that the good quantum number was k vector, right? Okay, so we have, let's say we have AK and AK dagger in K space, and now, for some reason, you'll see in the next lectures why, I want to switch to real space and define a creation operator of a particle at a state R, at the point R. Now you have to be a little careful about this, because R is not a discrete index, it's a continuous variable, and to create a particle at exactly a point R is a bit not well defined. In fact, you want to define something that if you integrate over a small region near R will give you a well-defined position. We, instead of calling it A of R, it is the convention is to give it another name, psi, and don't confuse, this is not a wave function, okay? It's a creation operator, but it's a creation operator that has units. while A and A dagger have no units, right? They're just pure numbers in terms of physical units. Psi has units in such a way that if you square it, you get density. Okay? So, psi dagger is, let me define it, is the sum over k. I'm using this formula, but now what will be my coefficients? Let me write it first like this. It's the overlap of the state k with state r, and this is what you're familiar with as phi k of r. It's the real space representation of the free particle wave function, right? And it is given by some normalization factor times e to the I k dot r. This I hope you all remember, very important, right? So it's this times ak dagger, okay? And what I wrote here is now about the normalization factor. You can choose whatever you like, but in such a state, yeah?
And it's supposed to be a factor that is the Fourier transform, right?
Right.
So where is it?
No, so this is, so when I apply, actually the normalization factor that you want to put.
It depends on k. At moment.
Yeah, but what I want here to take the convention that it's, you have some volume that eventually you may want to take to infinity. And the n is actually 1 over square root of the volume. Okay?
Yes, but what I'm asking, when you're doing Fourier transform, you have actual Fourier transform, for example.
What do I mean by actual? This is a Fourier.
You have the.
This is a Fourier.
If you're doing Fourier transform, for example, on the function f, you have f tilde that.
Right.
That is the Fourier transform, and that will be the coefficient of e to the ikr, right?
Yes, but here you're not transforming a function. Here it's not a function. So the analog. So it's exactly the thing. This is, these are the ak dagger are the Fourier components of psi dagger. Okay, if
but then you
let me first write it explicitly. Okay, so it's 1 over square root of volume, sum over k of okay, this is e to the I k dot r ak dagger. Okay, that's the Fourier. It's not a Fourier transform, it's the inverse transform, if you like. If that's, I don't know if that's what you meant, but you are transforming an operator to an operator. These are not functions,
yes,
they're operators.
But there should be also, if your statement is that is the.
That's a representation of the what I called psi dagger R. Okay. It's a representation, and yeah, and
why you can okay, I will say the question more specifically. Why those are the coefficients of a k?
Because I applied. This is a general formula,
Right.
and I just use the formula. Okay, I use the fact that the overlap of the state k with state r is the free wave function, free particle wave function.
Okay.
Okay, this is just what it is.
Yeah, for particles that don't have any potential, not under.
Yeah, free particle.
Yeah. Okay.
This is the wave function. It's an
For a system with
eigenstate.
no
These are
potential.
eigenstates of the momentum operator with with eigenvalue h bar k.
Okay.
Okay? So these are the field operator, these are local creation operators, and of course you can easily write what is the annihilation, local annihilation operator is sum over k e to the minus I k dot r times ak. Okay? And I can also write the inverse transform. If I want to represent ak dagger in terms of psi, then ak dagger is how you are going to do it. It's actually going to be an integral. So there is, let me see, I hope this is, yeah, so actually, yeah, okay, it's the same normalization factor, and there's an integral over space of e to the minus I, because it's the inverse Fourier transform of psi dagger. Okay? Okay, this has the right units because, because psi has units of 1 over square root of n, and a is pure. Okay, so it's just the inverse of this formula. Okay, okay, I think this is it, and next week, yeah.
Psi minus r is like the, I mean, it's like the transformation of a not that dagger. I mean, if I would want to use psi minus r.
Psi of minus r?
Yeah, I want translation.
Okay, yeah.
Backward.
Then
so
you put minus on it.
So it's like transforming a instead of a dagger.
Not really, because it's still a creation or annihilation, so you have to be careful.
Yeah, because I think for the formula here is correct. I mean, because
No,
just
the
minus
formula,
is different.
this formula is correct for any r, okay? Now, if you want to compare what is psi dagger of r and psi dagger of minus r, then in both cases you have a dagger here, but in one you have r, in one minus r. And then you'll get a cosine, for example, okay? But this formula this is the basic formula, that's the conversion. Now for here you can plug in any r and any k, okay? Okay, so next week we're going to start really playing the game. Okay, now we only learned about the tools, the machines, and next week we're going to see how we write operators of physical quantities and how we do calculations. Okay. Next week. כן, כן.
עוד דבר, כאילו אני כן רוצה רגע לשאול על המסלולים הפרואטיים של תלמיון, אז פשוט יהיה נגיד סוג של צורים משפטים כאלה, אבל פשוט נושא אותו כמו תלמיון, לא יודע.
בדיוק, זה לא... זה יהיה מספרים שנקראים גרסמן, אנחנו נלמד עליהם, אני מקווה. כלומר, נגיע אליהם, אני מקווה. כן.
פשוט אתה מציג את אותו אנטי-קומוטטור.
בדיוק, הם לא יכולים להיות מספרים רגילים. נכון מאוד. כן, אז זה גרסמן, כמו שאתה יודע, הוא הרחיב את לוח המספרים, כמו שאפשר להרחיב את המרחב.